Okay, welcome back to more GLS4OM, still working in Unit 7 techniques of integration. Today we're going to look at the method of partial fractions, but as is our new past practice, we're going to start with a little humor of the day. And this one is for MC Harge and Company. Hopefully you found the humor in that one. We got a jury of English majors here, so here is maybe our English teachers at St. Mary's, and I didn't do nothing. Ooh, a confession. But hopefully you saw the humor in that one. All right, moving forward. The method of partial fractions. When can you use it? I'm just going to make sure the pen's good to go. It is. So if you have a rational function, you can use this method of partial fractions. So it has to be a rational function. And remember, that means P and Q are polynomial functions. So we're not going to be seeing any of this kind of stuff. We will not be able to use partial fractions if it looks like that. So the exponents are going to have to be whole numbers. I mean, essentially what we're going to do in this technique is we're going to rewrite this quotient as a sum of two simpler quotients. So we rewrite this one rational function as a sum of two simpler rational functions. They tend to be readily integrated. Sometimes we have to do something else to get them there. The other definition we're going to need is we don't try to rewrite unless it's in proper form. And it's in proper form if the degree of p at x is less than the degree of q at x. So the degree of the numerator needs to be smaller than the degree of the denominator. And if it isn't, a simple long division will correct that. All right, so suppose that we have a rational function, and suppose it can be written as a product of n distinct factors. So we're going to take q at x, we're going to factor it. It has n potential distinct factors. Then what you can do is you can rearrange it as a sum of simpler rational functions in which we would have a constant over each. So a constant over the first factor plus a constant over the second, and so on all the way out to the end. So it's possible to do that. I'm just going to show you moving forward. So suppose we had these two simple functions, 2 over x minus 3 plus 3 over x plus 2. Getting a common denominator, we'd multiply 2 by x plus 2 and 3 by x minus, that should say 1 there. And then when we expand this, we're going to get 5x plus 1 in the numerator. We do, even with that correction I'm making there. Over x minus 2, or over x minus 1 plus x plus 2. So what does that mean? It means if we start here, that was this starting rational function that we were talking about over here. So we actually mentioned over here, there's that starting rational function. And that we're going to try to do now is write it as a sum of two simpler functions, which we can do right here. So we would take this integral of 5x plus 1 over x minus 1 times x plus 2. And then we can split that into two integrals. It can be the integral of 2 over x minus 1 dx plus the integral of 3 over x plus 2 dx. And these are readily integrable into lns. We do need to put absolute value around here. And the reason we need to put absolute value, let me just quickly try to explain that. In the original function here, we only have the restriction that x can't be 1 and the restriction that x can't be negative 2. X is allowed to be negative in this integral. So if we're going to find the area under the curve, we're looking for a function that's going to help us find the area under the curve, then we can plug in negative values. If we don't put absolute value around this ln here, then we're not going to be able to plug in negative x's because you can't take the ln of a negative number. That's the reason why you have to put absolute values around these here. So integrating, we would get 2 ln of the absolute value of x minus 1 plus 3 ln the absolute value of x plus 2 plus c as our integral. All right, now I'm going to walk you through a method showing you how you figure this out, and then you're going to try one. So the first thing you're going to do is attempt to factor that. An x squared minus 7x plus 10 factors into x minus 2 times x minus 5. And what we're going to try to do then is break it up into a constant over each factor. There are 2 factors here, just 2 of them here. If this was a cubic and there were 3 factors, then we'd have to add another plus c over and then the next factor, whatever that might happen to be. This one's just a quadratic. So we only need two simpler rational functions here. So now what I'm going to do is I'm going to really cross multiply by x minus 2 times x minus 5, if you like. And what will happen on this side, I will be left with x plus 2. And on this side, I'm going to get a times x minus 5 here, and I will get b times x minus 2. So that took us to here, and this is the equation we're going to work with. If I want to determine what a is, then I would allow x to be 2, because then this would drop out. So the first thing I'm going to do is let x equal 2 so I can find b. That will give me 2 plus 2 equals a times 2 minus 5 plus b. I just plugged in the 2 minus 2 just so that you could see that disappears. That's going to give me 4 is equal to negative 3a, and that gives me that a is negative 4/3. Now if I want to find b, I would like this piece to disappear, and that will disappear if we plug in 5, so I'll let x be 5. I'll get 5 plus 2 is a times 5 minus 5 plus b times 5 minus 2. That gives me 7 here and 3b, so b is 7/3. So what does that mean? It now means we can rewrite x plus 2 over x squared minus 7x plus 10, or in factored form x minus 2 times x minus 5. We can rewrite that as negative 4/3 over x minus 2 plus 7/3 over x minus 5. I'm going to leave this part as an exercise to you to verify that it is correct. So negative 4/3 times x minus 5 plus 7/3 times x minus 2, just getting a common denominator on that right hand side, all divided by x minus 2 times x minus 5. And so if you have done this correctly, then this needs to simplify to give you x plus 2. And let's maybe see if we could do that quickly. That's negative 4/3 plus 7/3 x. That's 3/3 x. There's our 1x. That's 20 over 3 minus 14 over 3 is 6 over 3 plus 2. So it does check out. My advice in university would be, if you have time, you should probably check to make sure that you are getting back to this side so you know that you have the correct a and b value. And then moving forward, we're now going to rewrite that negative 4/3. I'm going to put it out in front. Negative 4/3 times the integral of dx over x minus 2. And I'm going to write that 7/3 again, just showing you there were negative 4/3 and there were 7/3. I'm going to put the 7/3 in front of the next integral, plus 7/3 over the integral of dx over x minus 5. And again, these are lns. The antiderivative of this is ln of x minus 2, and the antiderivative of this is ln of x minus 5, and I've already explained why you need to put absolute value around there. If you don't put the absolute value in, then you're not going to be able to plug in certain negative values, because you can't take the ln of a negative, but the original function over here does allow for negative input. It's just not going to allow you to plug in a 2 or a 5. All right, now that you've seen how that works, you're going to try it in this one. And I was kind to you here. I gave this to you in factored form. In university, it might not be in factored form, and then you would have to factor it first. All right, it's time for our first time to ponder pause. All right, so the first thing we're going to do is make sure that you got the correct values, that we set this up correctly. So we're going to start with the integrand, which is 7x squared minus 17x minus 54 all over 2x plus 1 times x minus 2 times x plus 4. And now I'm going to have a over the first factor plus b over the second factor plus c over the third factor. We're going to try and break this up into the sum of 3 simpler rational functions, each one being a constant over each linear factor. That is doable. Cross multiplying. What will happen after we cross multiply here? We're going to get a times x minus 2. When we multiply this by this, the x minus 2 is going to go. We'll be left with b times 2x plus 1 times x plus 4. And when we multiply this by c over x plus 4, the x plus 4 will go, and we will get 2x plus 1 times x minus 2 times c. And now generally, I just start with the factors sort of one at a time. If I allow x to be 2, this would disappear, and this would disappear. So the a component of this and the b component are going to go when x is 2. So plugging in a 2, I've got 7 times 2 squared minus 17 times 2 minus 54. The b will stay. The a goes. I'm going to get 2 times 2 plus 1. times 2 plus 4. And of course I mentioned the c would go. All of this here becomes negative 60. This becomes 5 times 6, which is 30b. And dividing, we get b is equal to negative 2. So we found our b now. I'm then going to plug in an x of negative 4, because that will eliminate the a bit, and it will also eliminate the b bit, and I'll just be left with the c. So plugging in negative 4, 7 times negative 4, all squared, minus 17 times negative 4, minus 54. The c will stay, so we're going to get c, 2 times negative 4 plus 1, and then times negative 4 minus 2. All of this becomes 126. And this is going to become negative 7 times negative 6, which is negative 42. So we now have negative, I'm just going to pause for a sec because that's not matching up. I'm just going to punch that into my calculator again just to check I got the sign right. All right, resuming. This was a positive 126. However, I couldn't multiply negative 7 by negative 6 correctly. That would be positive 42. And that indeed is going to give us that c is positive 3. And now if I want to find a, I'm going to need to make those two factors disappear. And I will do that by allowing x to be negative a half. I'm going to plug that in as negative 0.5. So 7 times negative 0.5 all squared minus 17 times negative 0.5 minus 54. Punch all of that into your calculator. You will get negative 43.75. Now a is sitting up here, so a times 0.5 minus 2 times negative 0.5 plus 5. Again, punching that into your calculator, you'll get negative 1.5 times positive 3.5. That's negative 8.75. That's going to give you that a is 5. So we now know we're going to be plugging in 5 here. We're going to be plugging in negative 2 there. And we're going to be plugging in 3 there. So what I'm going to do again is I'm going to say it's a time to ponder pause, just in case you didn't finish this whole thing off. I probably should have asked you to do it in 2 steps. So I'm going to pause the video. I can't make you pause yours, but just in case you haven't finished. Okay, resuming and finishing off. So we have the integral. Actually, let's just look at splitting it into 5. We had a was 5, b was negative 2, and c was 3. So there is a, there is b, there is c. I'm going to use the linearity property of integrals, and I'm just going to write that as 5 times the integral of dx over 2x plus 1 minus 2 times the integral of dx over x minus 2 plus 3 times the integral of dx over x plus 4. These two are straightforward to go backwards on. That's just going to be negative 2 times the ln of the absolute value of x minus 2. This is plus 3 times the ln of the absolute value of, that should say, x plus 4. Now this one is a bit tricky because we have a linear, we're taking the ln of a linear factor that isn't monic. So if I were to take the derivative of the ln of 2x plus 1, I would get 1 over 2x plus 1. But then I'd have to multiply by the derivative of 2x, which is 2. So I'd have an extra 2 there. So instead of just putting a 5 out in front, I've had to put 5 halves so I can account for that extra 2 coming from the chain rule. So make sure you have 5 halves here and not 5. So this is 5 halves the ln of 2x plus 1. And in general, if you want to do the antiderivative of ax plus b, it is going to be the ln of the absolute value of ax plus b. And then we're going to have to divide that by a. All right, moving forward. So that was the simple case where everything factors into something linear, nothing repeats. The next case we're going to look at is what if we have repeated linear factors? So the other one was just distinct linear factors, nothing repeats. So x minus a1 could repeat up to m1 times, x minus 2 to a different number of times, and x minus a to the n up to m to the n times. So how do we work our way through this? We start with the first factor, and we do a11 over x minus a1. a12 over x minus a1 all squared. And then we keep going out to, this shouldn't say n, it should say m1, whatever this exponent was. So if this exponent was 4, we'd have something over 1 over squared over cubed, and then we stop at degree 4. We would repeat that for the next factor, and again we would end when we get to that factor, and that would be m2. That would be our last exponent. So if this was 5, degree 1 over a squared over a cubed over a quartic over the quintic, and this one here should be mn. All right, I'm going to walk you through an example of one of those. What would that look like? So I'm asking you to work on an integral again. They've been kind. It's already factored for us. So how is it different? Before we had a over x plus 2 and b over our second linear factor, but this linear factor is degree 2. So it's possible we could have combined something over x plus 5 and also something over x plus 5 all squared. And again, if this was x plus 5, let's say to the power 4, I would then have to add d over x plus 5 all cubed and e over x plus 5 all to the power 4. All right, we'll now proceed the same way we did before. Again, the new step here is we need an additional rational, simpler rational piece here because this was a squared. We're going to cross multiply by x plus 2 times x plus 5, and when we do that, we'll be left with a times x plus 5 all squared. When we do this here, we're going to get x plus 2 times x plus 5 in front of b, and when we work on the last one here, we're going to get c times x plus 2. And then we're going to study these and we're going to see what is it possible to determine. Well, if we let x be negative 2, this will go and this will go, and then I'll be able to find a. So let's start there. Plug in a negative 2 for x. Negative 2 plus 3 becomes 1. Then we're going to have a times negative 2 plus 5, and we need to square that, and the other two pieces become 0. That becomes 3. And if you square 3, you will get a 9. So a is 1/9. I'm going to leave b till the end because it's dependent on two distinct linear factors. If I allow x to be negative 5, this will go, and this one will go. So I'll just be left with c. So in order to find c now, I'm going to let x be negative 5. So I'll get negative 5 plus 3 from there. I get 0 from the a, 0 from the b, and now c times negative 5 plus 2. This gives me negative 2. This gives me negative 3 times c. And when we divide, we're now going to get c is 2/3. Now, how are we going to find b? So to find b, what we're going to do is we're going to sub in our value. We're going to replace this with 1/9. We're going to replace c with 2/3, and then we're going to pick an x value. Now, generally, you would pick an x value of 0, so I've shown you that on the bottom, because generally that makes everything work much simpler plugging in a 0. You just get a 3, you'd get a 5, you'd get a 2, you'd get a 5, and you'd get your 2 from here. But then that left me with fractions. That left me with 3 is equal to 25/9 plus 10b plus 4/3. I'm now going to multiply by 9 to clear those fractions. I got 27 equals 25 plus 90b plus 12. That gives me negative 10 equals 90b, and that's how I got b was negative 1/9. So usually I use 0, but what I decided to do instead was to plug in 1, because when you plugged in 1, everything cleaned up nicely. I ended up with 4 here, 1/9, that became 6 squared. This becomes 3, that becomes 6. And that becomes 3, and everything is just going to divide out nicely. 36/9 becomes 4, that becomes 18b, that becomes 2. And then I got to negative 2 is 18b, so b is negative 1/9. So that's just illustrating. It doesn't really matter what you plug in for x. As long as it is not -2 or -5, because that's going to make the b drop out. Once you found a and c, it will not matter what you choose for x. Usually pick a value that makes your calculations easier. So then this will be replaced with 1/9 when we move forward. This is going to be replaced with -1/9 when we move forward. And this one is going to be replaced with 2/3. So moving forward now, we've got the integral of 1/9 over x plus 2 minus 1/9 over x plus 5 plus 2/3 over x plus 5 all squared. Linearity property of integrals allows me to split this into 1/9 the integral of dx over x plus 2 minus 1/9 the integral of dx over x plus 5 plus 2/3 the integral of dx over x plus 5 all squared. The first two, the antiderivative of the first two will be lns. So this is going to be 1/9 the ln of the absolute value of x plus 2 minus 1/9 the ln of the absolute value of x plus 5. These were monic here, so I don't need to divide by the coefficient of x. Now going backwards on this one, this is x plus 5 to the -2. And to go backwards on a power function, we add 1 to the exponent, and then we divide by that. So that's going to become x plus 5 to the -1 divided by -1. So that's how I got -2/3 x plus 5 to the -1 plus c. So when you go backwards on these, you should end up with power functions possibly here. Or when the exponent is 1, when you go backwards, you have to remember those are lns. All right, so now you're going to try this one, and this time I think I'm going to suggest we split it into 2 parts. It is going to be a lot of work to try and find your A, B, and C. I do not think I mentioned when we found this A, B, and C that we probably, if we had time, if this was in university, getting your common denominator, but this one would not be, this would be a lot more work. It'd be 5 times x minus 2 times x plus 4 minus 2 times 2x plus 1 times x plus 3 plus 3 times 2x plus 1 times x plus 2. And simplifying all of that, you got to get back to that quadratic. So you may or may not have enough time to do all of that in university. So maybe just double check your work here before you move forward. All right, so moving on to this one, we're going to start with why don't you find the values of your constants, however many you think you need, AB, ABC, ABCD. And that will be up to you to decide. So it's a time to ponder pause. All right, so resuming on this one, we're going to have 3x minus 9 over x minus 1 times x plus 2 all squared. So a over, the first linear factor doesn't repeat, so it's a over x minus 1. The second linear factor repeats twice, so it's b over x plus 2 plus c over x plus 2 all squared. And I'm going to try and go a bit faster now. After we cross multiply, we will get to here. 3x minus 9, a times x plus 2 all squared, b times x minus 1 times x plus 2, and c times x minus 1. If I allow x to be -2, the a's and the b's will drop out. And what you will see is you're going to get -15 from the left-hand side. You're going to get -3c from the right-hand side, and that's going to tell you that c is 5. So hopefully you got that c was 5. If I plug in an x of 1, the b and the c components here will drop out. Those parts will drop out, and I'll just be left with a. So plugging in a 1 on the left-hand side, we will get -6. Plugging in a 1 on the right-hand side, we will get 3. When we square that, we will get 9. So I'm going to get -6 is 9a, and that gives me a is -2/3. And now to find the b, what we're going to end up doing is plugging in the 5 for c and the -2/3 for a. And then we pick whatever x value we wanted. Generally, I usually pick 0. And in this case, I am picking 0. So doing our work here, plugging back into here, if I choose 0, because usually it makes life simpler, we're just going to have a -9. Here we're going to have 2 squared, so -2/3 times 2 squared. You're going to get b times -1 times 2. You're going to get 5, because that's what c is, times -1. So that's where all of that came from. That gives you -9 is -8/3 minus 2b minus 5. I just multiplied by 3 to clear the fractions. -27 equals -8 minus 6b minus 15. Grouping like terms, you'll get -4 is -6b. I now have that b is 2/3. So again, I think the worst part of partial fractions is doing all of this algebraic manipulation right here in order to find the correct values for a, b, and c. Now that you have the correct a, b, and c, the next step for you is to integrate this. So another time to ponder pause. All right, so resuming, we're going to see when I move to the next slide, we're going to have the integral of -2/3 over x minus 1 plus 2/3 over x plus 2, and then we're going to have 5 over x plus 2 all squared. And I might just simply have jumped straight to -2/3 times the integral of dx over x minus 1 plus 2/3 times the integral of dx over x plus 2 plus 5 times the integral of dx over x plus 2 all squared. And that's exactly what I did here. You don't necessarily need to write that other step in. Going backwards, this is a ln, it's monic, so it's just going to become -2/3 times the ln of the absolute value of x minus 1. This is also monic here, degree of the x term is 1. So it's just going to become plus 2/3 the ln of x plus 2, the absolute value of x plus 2. And then going backwards on this one, this is a power function, it's x plus 2 to the -2. If I go backwards, I'm going to add 1 to the exponent. I'm going to get x plus 2 to the -1, which is 1 over x plus 2. And then I'm going to need to divide by -2 plus 1. So that -5, or the +5 out in front, has now become a -5. And that's how we got to -5 over x plus 2. And then don't forget the plus c. And I hope I didn't forget it in the other places. All right, so we did one now where all of the factors were linear, non-repeating. Example 2 was linear. All were linear, but some may repeat. Now what we're going to take a look at is what if you're irreducible, which means not factorable, your roots would be complex numbers. How are we going to handle that? And so every time you have a linear factor like these, we're just going to use constants a, b, c, and so on. But once you get an irreducible quadratic, then you're going to put a linear over it. We have a constant over the linear, and we have a linear over the quadratic. And I imagine we could extend this to something if these were cubics here. If this was a cubic, then the function in the numerator would have to be a quadratic. So every time you have an irreducible quadratic, you're going to put a linear factor in the numerator. When we do them now, what could end up happening is you now might have to be taking the integral of dx over x squared plus a. This is an arctan. I'm not sure if you recognize it as an arctan, but I put this slide in here just to show you. And the integral of this would become 1 over the square root of a, the arctangent of x over the square root of a, and then I threw in the constant. So we've seen that we could have lns, that we could have going backwards on power functions, and now it's possible that we might have arctans in these. All right, I'm going to walk you through an example. So we have the integral of 4 dx over x cubed plus 4x. The first thing I'm going to do is factor out the x. Then I'm left with x squared plus 4. X squared plus 4 is definitely irreducible. That is not factorable. It has complex roots. So I'm going to put a over my linear factor. It's not an a squared or an x squared. If it was an x squared, I'd have a over x plus b over x squared. This x has degree 1, so simply a over x. The irreducible quadratic now, we will introduce this in its numerator. We'll introduce bx plus c divided by the irreducible quadratic. And now we're going to multiply by x times x squared plus 4 on both sides to clear out the fractions. And that will leave me with 4 on the left, a times x squared plus 4 plus x times bx plus c. All right, now what are we going to do? If you allow this piece out in front, whatever it might be, it could have been x minus 1, it could have been x plus 2, but we want to zero out this factor, because if we zero out this factor, this disappears. So I chose to start by letting x be 0 to clear out the bx plus c. So if x is 0, I'm going to get 4 is equal to a times 0 squared plus 4. And of course plus 0 for that bit. That gives me 4a, or 4 is 4a, so I now knew that a was 1. Now it's a little bit tricky to work on the next piece. So we now know a is 1. So what we're going to do is plug in a 1 here, and we're going to get 4 is equal to x squared plus 4. If I distribute here, I will get bx squared plus cx. And then I'm going to write this in quadratic formation. I want to know what the coefficients of each terms are, and I choose to write it in descending order. So I'm looking at the left side. If you had me for advanced functions, I know we did some of these already. I'm going to look at the left side. We did some challenging assignments. And this is a constant on this side, so it really is 0x squared plus 0x plus 4. See it that way. If we see it that way, then when we get an x squared and an x squared, so we have 1 plus bx squareds, we have plus cx, and we have plus 4. And that's telling us now that we have a 0x squared on the left, so 1 plus b needs to be 0. We have a 0x squared, and we have a 1 plus bx squared on this side. So 1 plus b needs to be 0. We have a 0x on the left side, and we have a cx on the right side. So that tells us that cx must be 0. I'm going to cross that off. That should just say that c needs to be 0. There should not be a 4 there. So c needs to be 0. And now b is negative 1. So coming back up to here, we know this is 1. And we know this is negative x plus 0. And then we're going to split that into two separate integrals. Again, I'm just going to repeat. When we have irreducible quadratic factors, it makes finding the next two pieces here just a little bit more challenging. You can't find it by plugging in a value for x. What you do is you find the value for this piece here. Then you expand, you collect like terms, and you find the coefficients of each one of the x squared term, of the x term, and the constant, and then you make sure they match on the left and right hand side. So moving forward now, we have the integral of 1 over x plus negative x over x squared plus 4. Split that into two integrals, 1 over x dx minus x over 2x plus 4. We're not going to be using an arctan on that. I'm going to have to do a substitution on this. So in my substitution, I'm going to say, let u be x squared plus 4. Then du over 2. We can say du is going to be equal to 2 dx. 2x dx. I dropped my x. So du would be 2x dx, and du over 2 would be x dx. So I can just replace this with du over 2. And that's what's happened right there. I left the negative where it was. I'm going to replace x squared plus 4 with u. So we may have to use the technique of substitution as well. All right, going backwards on this one, the integral of 1 over x dx is just the ln of the absolute value of x minus, this has become, maybe I'll just write it this way first, 1/2 the integral of du over u. And going backwards on du over u, that will just become the ln of the absolute value of u. Then my plus c. And then I will back substitute the x squared plus 4. So in the end, we have the ln of the absolute value of x minus 1/2 the ln of, that is not correct. There should be absolute values right there. Actually, do I need the absolute value in this case? Let's think that one through. If you plug in a negative x and you square it, it will become positive. So the lowest that x squared plus 4 can be is 4. So the absolute value this time were not needed. So round brackets would be fine here because the argument there is never going to become negative. All right, let's have you try one of these now. So you've got your linear factor right here, and there is your irreducible quadratic. Let's do this in two parts. Part 1, find the values of your constants. And again, a time to ponder pause. All right, so taking this one up, finding our constants. So I'm going to have 18 over x plus 3 times x squared plus 9. the linear factor has just a constant over it, a over x plus 3. The irreducible quadratic is going to have a linear over it, so it's going to be bx plus c over x squared plus 9. And again, I said if you had an irreducible cubic, then it would be dx squared plus ex plus f. You can step these up to any level of complexity. Hope they're not too complex when you get into university. So again, if we multiply by x plus 3 times x squared plus 9, just to clear all the fraction pieces, we're going to get 18 equals a times x squared plus 9. And we're going to get bx plus c times x plus 3. First thing I'm going to do is find a. And to find a, I want to let this factor become 0. This factor will be 0 when x is negative 3. So that was my starting point. Let x be negative 3. I'm going to get 18 from here. Negative 3 all squared plus 9. That becomes 9 plus 9. That's 18. So I get 18 is equal to 18a. And a is 1. All right, now moving forward, how are we going to find what b and c are? So we're going to start with noting a was 1, so imagine plugging in a 1. 18 is equal to 1 times x squared plus 9. And then I'm going to expand this part here. So bx times x is bx squared. Bx times 3 is 3bx. There's plus cx, and there is plus 3c. And then I'm going to group them. So these two come together, factor out the x squared, and I'll get b plus 1 times x squared. These are my terms in x right here. So if we factor the x out, we will get 3b plus c times x. And the two constant pieces on the end are sitting right there, plus 9 plus 3c. Now, what do we see on the other side? I'm going to see the other side is 0x squared plus 0x plus 18. So now what do I know? I know that b plus 1 needs to be 0 because there's 0x squareds on the other side. I know that 3b plus c needs to be 0 because there are 0 x's on the other side. And I know that 9 plus 3c needs to be 18 because I have 18 units on the other side, or the constant is 18 and the two constants need to be equal to each other. b plus 1 is 0 gives me that b is negative 1. If we isolate here, we're going to get 3c. 18 minus 9 is 9. 3c is 9, so c is 3. We now know that c is 3 and b is negative 1. And then these values should also satisfy this last equation. We had a system of 3 equations and 2 unknowns. All of them need to be true simultaneously. So 3 times negative 1 is negative 3, plus c, which is 3, gives us negative 3 plus 3, which is 0. So we are satisfying that equation. So we now know that this is 1, and this becomes negative x plus 3. So then we can split this into the integral of 1 over x plus 3 plus the integral of negative x plus 3 over x squared plus 9. And again, I did ask you to split into 2 parts, so just in case you didn't finish off the whole thing, it's another time to ponder pause. Okay, resuming on this one, as I had mentioned previously, we're going to split this up into the integral of a was 1, so 1 over x plus 1, plus b was negative 1 and c was 3, so we're getting negative x plus 3 over x squared plus 9 dx. I'm now going to split this into 2 because this is negative x over x squared plus 9. Undoing our common denominator, if you like, plus 3 over x squared plus 9. So I'm going to split that using the linearity property of integrals into dx over x plus 3 minus the integral of x dx over x squared plus 9 plus 3 times the integral of dx over x squared plus 9. This one will be straightforward to back up on because that'll be ln. This one to back up on, I'm going to need to do a substitution. I'm going to let u be x squared plus 9. du is 2x dx, so 1/2 du is x dx. So the x dx is being replaced with the 1/2 du, and the x squared plus 9 is being replaced with the u. And then when we come to this one now, we're going to think about what's this one. This is our arctan one, which coming from there. That's the arctan one. I said those can pop up. So that's popping up in this case right here. So going backwards on this one, it's the ln of the absolute value of x plus 3. And I need the absolute values in this case, because it's possible for x to be negative enough to make the whole argument negative. This is minus 1/2 the ln of the absolute value of u. I'm plugging in u, which was x squared plus 9. Now technically the absolute value not needed here, because the lowest x squared plus 9 can be is 9, and that certainly isn't negative. But I put them in for good measure, but I know they're not needed. Going backwards on this one, we had minus 1 over the square root of a. Now a right here, there is a from that formula. Again, just showing you where that formula was. I'm doing 1 over root a, the arctan of x over root a. So the 3 is coming from here, so it's 1 over root a being 9. 1 over root a, the arctan of x over the square root of a being 9. This becomes 3 over 3, which is 1. So minus the arctan of x over 3 plus c. And that was how that one laid out. All right, only a couple more slides to go now. This one is a long one. I did mention at the beginning, in a proper rational function, the degree of the numerator has to be less than the degree of the denominator. If it is a proper rational function, it can be resolved into partial fractions. So if the degree of the numerator is larger than the degree of the denominator, you're going to have to divide first before you proceed. So for example, in this case, we have the integral of x plus 4 over x plus 2. The degree of the numerator is not smaller than the degree of the denominator, so I did a long division over here. X plus 2, x goes into x one time, so I get x plus 4 minus x plus 2. That gives me 0x plus 2. So it's possible to rewrite x plus 4 over x plus 2 as 1 plus 2 over x plus 2. So splitting into two integrals, I have the integral of 1 dx plus the integral of 2 over x plus 2. Going backwards on dx, we will get x, and going backwards on this, we will have 2 times the ln of, and technically we would need absolute value around that. So I'm going to put the absolute value there. And now this was a definite integral, so to evaluate it, evaluating at the upper bound minus the lower bound, the first bit's 4 minus 2. The second bit becomes plus 2 ln of 4 plus 2 is 6, minus 2 times ln of 2 plus 2 is 4, minus 2 ln 4. And now 4 minus 2 is 2. I get 2 plus 2 ln 6 minus 2 ln 4. And I'm noting that I could rewrite that as 2 plus 2 ln of 3/2. And eventually I could take it to the ln of 9e squared over 4. I'm going to leave it up to you to verify why that is indeed correct. If you're having trouble doing that, you can always send me a message and I will show you how you take it to there. I'm going over that because sometimes in university they will give you this and they will tell you, demonstrate that this definite integral evaluates to the ln of 9e squared over 4, and then you'd be expected to show that. All right, one last question. So a student was asked to evaluate this. They took a look. They said they can use partial fractions on this because 12 is polynomial. The denominator is polynomial. And as far as partial fractions go, they split it up this way. Last thing you're going to think about in this lesson is, have they made any errors? And this is our last time to ponder for today. All right, taking this one up. The mistake the student has made is bx plus c over x squared minus 16. You only do that if this isn't irreducible. But it turns out that x squared minus 16 is factorable, so the student has made a mistake. They cannot do it this way. They're going to need to factor. So factoring, we get x plus 4 times x minus 4. That's going to give me x plus 4 all squared times x minus 4. So if we factor this, we will get to here. And now, according to the method or technique I showed you for partial fractions, we should be splitting this up into a over x plus 4 plus b over x plus 4 all squared plus c over x minus 4. If you want to, you could actually completely finish this off and integrate it. You can find the solutions to that online. I haven't done that here because they didn't ask us to. They just asked if there were any errors. All right, that takes us to the end of Lesson 5, Partial Fractions. If you made it to the end, good for you, because this one was a bit on the longish side. So if you made it to the end, once again, thank you for watching. Don't forget to like and subscribe. Stay safe and take care, and we will see you next time.